Section 4.4, theorems about zeros of polynomials. The objectives here is to find the polynomials with specified zeros for the polynomial function with the integral coefficients. Find the rational zeros and the other zeros if possible. Use Descartes' rule of designs to find information about the number of real zeros of the polynomial function with real coefficients. Okay, the fundamental theorem of algebra. Every polynomial function of degree n with n being greater than or equal to 1 has at least one zero in the set of complex numbers. So find the polynomial function of degree 3 having zeros of 1, 3i, and negative 3i. So what does this tell me? That to have the positive 1, I know originally it was x minus 1, because it would have been this, right? And subtract the 1 from both sides. Now we have it in factored form. I have a positive 3i, so we know it's going to be x minus 3i. And I have the negative, so I know it's x plus. And again, just to remind you, if we're saying x is equal to that 3i, x is equal to negative 3i. Now we'll get it in the factored format. Okay, so, and that's where they came up with this. Knowing that, now I can say, okay, my coefficient, my leading coefficient here is a subscript n is times these factored forms, can be non-zero numbers. The simplest polynomial function will be obtained if we let it be 1. Now, this is when multiple factors we obtain. So here we go. I notice this is in its factored form. This one here, we could probably do a little bit more work to it. So let's do it. I know that I squared is equal to negative 1. So when I take that x minus 1 times x squared minus 9 times negative 1, now I get x minus 1 times x squared plus 9. All right, so now we got it written in the format we need it. So what I'm going to do is distribute, okay? So I got x times x squared. I got x times that 9. I got negative 1 times x squared. Negative 1 times that 9. And let's just clean it up. X times x squared is x cubed. Remember, when you multiply like bases, you add the powers. I'm just going to rewrite this as 9x. I have negative times positive, so it's a negative x squared, and negative times positive. Put together any like terms. Don't see any like terms here, but however, I do see it's not written in descending order all the way, so let's write it. X cubed is the leading term. Then we have x squared next, plus the 9x minus the 9. Now, non-real zeros, a plus bi, where a is the real part, bi is the imaginary, and we can have a minus the bi, where b cannot equal 0, because if b equals 0, then it's all real. There's no imaginary to this. The conjugate of a minus bi would be a plus bi. If it's a plus bi, the conjugate to that would be a minus bi. That's why they said, for example, we have 2 plus 7i, and what would be the conjugate? Well, the conjugate would be the 2 minus 7i. Okay, irrational, which makes sense. C times the square root of b. Whenever you take the square root of a number, we know that the square root of 4 is 2, but it don't always come out pretty. The square root of 2 would actually be some decimal number, and it's not going to come out real pretty, so it's irrational, right? It's not going to be a perfect square. It will not be a perfect square. Irrational will not be. All right. Suppose that a polynomial function of degree 6 with rational coefficients has a negative 2 plus 5i, negative 2i, and 1 minus square root of 3 as 3 of its zeros. Find the other zeros. Since the coefficients are irrational, other zeros are conjugates of the given zeros. Okay? So there are no other zeros because the polynomial function of degree 6 can have at most 6 zeros. So let's just solve some without actually talking a whole lot. And we still got a little bit more to read, and then we're going to solve some. It says, let this polynomial function, so we've seen this notation before, where all coefficients are integers, consider a rational number denoted by P divided by Q, where P and Q are the relatively prime, having no common factors besides a or -1 and 1. If P divided by Q is a 0 of P of X, then P is a factor of A naught. That's what this is called. And Q is a factor of A n. So right here is my Q, and right here is my P. And this is finding the rational zeros theorem. So here we go. We're going to find all possibilities of zeros. All right. So what we would do, it says find the rational number of zeros, and then we have to check to see if they are true. So to find it, we got our Q and we got our P. So I can rewrite it as P over Q, which in this case is -4/3. What does that tell me? That tells me plus or minus 1, plus or minus 2, plus or minus 4. What do I know about that? I know that 1 times 4 is 4. I know that 2 times 2 is 4. So I wrote down the factors of them. Now let's look at Q. Well, Q is prime, so it's just going to be plus or minus 1 and plus or minus 3. Okay, so those are my prime factors. And now what I need to do is determine all possibilities. So I got plus or minus 1 divided by plus or minus 1. So I know that I'm going to have a possibility of a positive 1 and a negative 1. Then, and so, you know what, let me not skip this step. I know down here at the bottom they're showing you, but I want you to see how we get it. All right. So this is basically saying we have plus 1 over plus 1, right? We have plus 1 over -1. We can say -1 over plus 1. We can say -1 over -1. What does these outcomes give me? It gives me a positive 1 and a negative 1. Next, it said that I can have positive 1 over positive 3, and I can have positive 1 over -3. I can have -1 over positive 3. I can have -1 over -3. What does it tell me? I have a possibility of a positive 1/3 and a possibility of a negative 1/3. So I wanted you to see what I was doing. I took this over that one, and now I took this over that one. Now let's go to the 2. Let's do 2 next. So now I have a positive 2 over positive 1, -2 over positive 1, a negative, or positive 2 over -1, and a -2 over -2. So that tells me I have a possibility of positive 2 and -2. Now let's take that 2 over the 3. I have a possibility of positive 2 over positive 3. Possibility of positive 2 over -3, a possibility of -2 over positive 3, and a -2 over -3. So that means I have a possibility of positive 2/3 and a -2/3. Now our last one, we have 4 over 3. So let's try it out over here. Positive 4 over positive 3. Positive 4 over -3, -4 over positive 3, negative over negative. Okay, so now I know I have a possibility of a positive 4/3 and a possibility of a -4/3. So Now that I've found all possibilities of zeros, I need to figure out which ones are my zeros. So you can use synthetic division. We can plug these numbers back in this function. So we can say function of -1 and then plug in everywhere as I see x, the -1. What is the outcome? We can do the same for all of them. Again, either way it goes, as long as you do your math right, you're going to get your answer right. So you can use synthetic division or you can plug in. And as you notice, they've done it on these. If you get, you could come out with a complete factorization and can give us something irrational. Okay. Now let's talk about Descartes' rule of signs. If my polynomial function p of x with real coefficients in a non-zero constant term, the number of positive real zeros of this function is either the same number of the variations of the polynomial or less than the number of variations. If that's by a positive even integer. The number of negative real zeros is either the same number of variations, so we get this, or less than the number of variations, okay? So a zero multiplicity m must be counted at m times. So what does Descartes' rule signs tell us about the number of positive real zeros and the number of negative real zeros? The number of variations of the sign in p of x is 2. What does that mean? That means we got a positive that went to negative. Well, negative stayed to negative. That didn't change, but we got a negative that went to positive. So we have 2 sign changes. We have a sign change here and a sign change here. So we have 2 possibility of real zeros or less than 2. So here we go. If we had -2 to -5, that's no sign change, but negative to positive here, that's 1. And then positive, positive, so we only have 1 possibility